Hi, everyone. Thank you for joining us today for this webinar, Getting Started with Serverless. My name is Rob Sutter. I'm a Senior Developer Advocate on the Serverless team here at AWS. Today, our goal is to get you started with Serverless and give you the tools that you need to build your first web application with Serverless. To get you there, we're going to cover a couple key points. First, we're going to go over what is serverless. What do we mean when we talk about an application being serverless? And then we're going to elaborate by providing some specific serverless concepts, both what does it mean to be a serverless application and how do we build with serverless. We're going to cover some execution models of serverless applications and design patterns. We're going to talk about pricing considerations when you're building your serverless application and how those relate to resource allocation. We're going to talk about permissions, identity and access management, so that you can control both what has access to your application and the resources that your application itself can access. We're going to cover Amazon API Gateway, a key service for building your serverless web application. We're going to discuss some tooling that's available to help you build more effectively and more efficiently. And then finally, we're going to cover some basic observability so that you can understand what is happening with your web application, how your users are using it, and how you can improve it. Before we begin, a little bit about myself. The most important thing for you to see there is that my email address is there for you to contact me, and my Twitter DMs are open as well. So if you have questions about this or other serverless building at AWS, please get in touch. My goal is to help you build on AWS as effectively as you can, so please let me help you. I'd also welcome any feedback you can provide that can help us improve our services. So, as we said, the first thing we'll discuss is what is serverless. What do we mean when we say that an application is serverless? And when we talk about serverless applications, we talk about them in 4 key dimensions. First, there's no infrastructure to provision, no infrastructure to manage. You don't have to worry about servers, containers, operating systems, or patching. All of this is handled by us behind the scenes for you. The second domain is that it scales automatically. This means that your serverless application will scale by a unit of consumption or unit of work. That means as you have more work to do, the underlying resources scale automatically without any intervention on your part. The third domain is that you pay for value, and this is closely related to that automatic scaling. The billing model is that as you consume more resources, you pay at that point. You don't pay in advance for resources that remain unused. And finally, the fourth domain is that it's highly available and secure. This is because we are managing that availability for you, as well as the security. The operating system patching, the runtime patching, these types of things that you would normally consider in the past, you no longer have to deal with those. These parts of the AWS shared responsibility model are now assumed by AWS, leaving you free to focus on your application and deliver more features more quickly to increase your customer satisfaction. So, with those 4 key domains in mind, what does serverless mean for you as a builder? Serverless gives you these competitive advantages. It gives you greater agility, the ability to use the scarce resources that you have to experiment more by freeing you from working on functionality or non-customer facing functionality that you would have used in the past. It means less operations for you as a developer. You don't have to worry about those operating system patches. You don't have to worry about network configuration and these other type of considerations because they're managed for you. And that leads to a greater focus on your product. Focus on your product is what gives your customers satisfaction. It's what distinguishes you from your competitors. That ability to deliver more value to your customers more quickly. Also, if you're building for the first time, that faster time to market helps you outrun your customers. You can get an experiment up and running and start getting feedback from the users that matter more quickly by building a serverless application. And finally, it means that your costs will grow with your business. You can put an experiment out there, and if customers don't use it, you don't pay for it. But if it becomes wildly popular, then you know that that's an area that you can focus on your customer feedback and growing your business. So when we talk about serverless at AWS, the most important service to understand is AWS Lambda, and that's going to be the focus of today's webinar. AWS Lambda sits at the center of several trends in computing. First, there's event-driven computing. Rather than an imperative model where you walk through a program executing commands, event-driven computing responds to events. It's reactive. There's also functions as a service, which is when a service provider offers the ability for you to execute functions or code without worrying about the underlying complexities. And finally, there are serverless function as a service platforms. AWS Lambda is all three of these things. Lambda handles load balancing for you. Automatically, requests come in and are routed to instances that are available to support that request. You no longer have to provision load balancers or worry about the network routing between them. Lambda handles auto-scaling for you. If you don't have enough instances provisioned to handle requests, we will transparently provision that for you behind the scenes so that incoming requests can be handled. Lambda handles failures for you. If the execution environment should go down while it's executing your request, we handle that retry. It handles security isolation, keeping the memory and compute that you use separate from the memory and compute that other customers use. It handles operating system management, applying underlying security patches. Even patches that have to be applied at the hardware level are managed for you. And it manages utilization for you, closely tracking your usage and your billing. It also does a number of other things for you. And for more information on that, I'd encourage you to see the AWS Lambda homepage. So that's what serverless is. But what are some of the serverless concepts that we will use to build with? Well, as I mentioned, it's important to understand AWS Lambda. We will build our serverless applications around AWS Lambda. And the basic unit of compute with AWS Lambda is a function. A Lambda function can be written in one of the 6 provided runtimes, or you can even provide your own runtime. We've had customers create runtimes in languages from COBOL to Rust, proving that the whole spectrum of compute over decades is available and works on Lambda. The basic model, as we mentioned before, is event-driven. An event source happens that invokes your function. That event source could be a change in data state, for example, a change to an item in DynamoDB, or an object that's uploaded to an S3 bucket. It could be a request to an endpoint on API gateway that triggers your Lambda function invocation. It could also be a change in a resource state. For instance, AWS config allows you to provide rules, and when a change occurs in resources that are managed by those rules, you can capture that change with a Lambda function. Once your function has been invoked, your Lambda function can interact with other services. These can be downstream AWS services, such as DynamoDB or S3, or they can be any resource that you can access from your AWS account, including via HTTP calls to third-party providers. It's one thing to talk about an event-driven cycle. It's another thing to see it. So let's go into the AWS Management Console for a quick demo. In the AWS Management Console, you'll find the Lambda console underneath Compute in all services, or you can simply search for Lambda. On the Lambda dashboard, let's create a function. We'll start with one from scratch so that we get a simple hello world example. Give a name to your function. In this case, we'll say my function, and select a runtime. As we mentioned before, there are 6 core runtimes with different versions that are supported, or you can provide a custom runtime yourself. For this example, we're going to use Node.js 12. Choose Create Function in the bottom right, and AWS Lambda provisions the resources for your function behind the scenes. Success! Our function has been created. At this point, we're looking at the designer. Over here on the left are where we can add triggers that would invoke our function. These are the event sources we mentioned earlier, like API gateway, an application load balancer, or other AWS services. Let's look at what our function does. Further down, we have the code window. In the code editor, we have a simple Node.js function that receives a request, creates a response, and returns that response to the caller. This is a great example of a Lambda function that would be interacting with API Gateway, for example. To see how this works, we can create a test event. We don't need to change any of these values, so we can simply give our event a name and choose Create. Now we can invoke our Lambda function here at the code editor or here at the top of the Lambda console. We see that our execution was successful. And just as expected, we're returned an object, a simple object with an HTTP status code of 200 and a body, hello from Lambda. If we return to the functions page, I'd like to show you one thing that you can use when you're exploring further. Choose Create Function, but this time choose Use a Blueprint. Note that you can filter the available blueprints by runtime or by keyword. In this case, we could choose to filter the available blueprints by Python 3.7, Python 2.7, or again, Node.js 12. In this case, we see that we have a simple mobile backend as an example, or DynamoDB streams processing, or a number of other examples. It's beyond the scope of this webinar to explore these right now, but again, I'd encourage you to return here and explore blueprints as you're learning how to create your application. Now that we've created and executed a Lambda function, let's look at how it's structured. The first thing to note is that the Lambda function has a handler. The handler function is the function that will be executed when our Lambda function is invoked. In this example from Node.js, that's the exports.handler function. The second thing that you should notice about this Lambda function is that it receives an event object. The event object contains all of the data sent from your event source to your Lambda function during the function invocation. For example, for an API gateway request, this would contain the information that was sent via HTTP. Finally, we have the context object. And the context object provides you a number of methods that allow you to interact with runtime information specific to that Lambda function. This is metadata about your Lambda function and its execution environment. So now that we've looked at the structure of AWS Lambda functions, let's look at some execution models. There are 4 key ways that Lambda functions can be invoked. First, Lambda functions can be invoked directly using the Lambda API. This is the API provided by the Lambda service, and it's used by all of the other AWS services that invoke Lambda functions across models. It supports both a synchronous and an asynchronous invocation model, and it can pass any event payload structure you want. This is where you would invoke a Lambda function directly in your code and then either wait for the response or move on. This client is included in every SDK that AWS publishes. The 3 most common execution models for invoking Lambda functions are the synchronous model, the asynchronous model, and a streaming model. The synchronous model is a push-based model, such as with Amazon API Gateway, when a user requests data from an endpoint, and that response holds or stays open until the Lambda function completes execution. At that point, the Lambda function returns its response, and it is passed back to the caller, ending the execution. In an asynchronous model, the invoker passes the event into AWS Lambda, which passes it to a function and immediately returns before execution completes. This occurs, for example, whenever an Amazon SNS topic receives a message or an object in Amazon S3 changes. Finally, you have the streaming or poll-based model. For example, you can poll Amazon DynamoDB for changes or Amazon Kinesis for changes in your stream. These will be passed into the AWS Lambda service in collections of items, which would then be handled by your function. In addition to web apps, there are several other common AWS Lambda use cases that we see. You can think of a static website or a complex web app, but you can also think of mobile backends, for example, or backends for traditional client applications. These can be built, again, using API Gateway connected to AWS Lambda functions. AWS Lambda is also useful for data processing, both in real-time events or MapReduce applications. Chatbots are commonly built with AWS Lambda functions, and Amazon Alexa skills are built as well. In fact, the Alexa Skills Kit provides an SDK for you to interact with AWS Lambda. Finally, a common use case for AWS Lambda is for IT automation. For example, policy engines can invoke AWS Lambda functions whenever they receive a violation or simply need to test a resource. They're also used to extend native AWS services or to manage the infrastructure that you're currently running in your account. As we mentioned at the beginning, you have a number of controls over pricing and resource allocation that track specifically with usage of your Lambda function. AWS Lambda usage is priced using a fine-grained model. You buy your compute time in increments of 100 milliseconds. There's a low per request charge. There are no hourly, daily, or monthly minimums, no device fees, and you never pay for idle. Now, there's a star there that we've added recently because of a feature called provisioned concurrency that allows you, in some cases, to reduce your Lambda spending, as well as reducing cold start times. We'll discuss provisioned concurrency later in this webinar. It's important to note that there's a free tier for AWS Lambda as well. Every month, every customer receives 1 million requests and 400,000 gigabyte seconds of compute. A gigabyte second is 1 gigabyte of allocated memory executing for 1 second, or 10 increments of 100 milliseconds. And it's the unit of measurement for pricing for AWS Lambda functions. Lambda exposes only a memory control for changing your function's compute power. That memory control allocates a proportional amount of CPU core and network capacity, depending on how much memory is allocated. This means that if your code is CPU, network, or memory bound, it could actually be cheaper for you to execute your Lambda function with more memory. For example, look at these executions and runtimes. The cheapest allocation in this case was 128 megabytes of memory, the lowest available amount of memory to execute a Lambda function. However, performance-wise, 1,024 megabytes was the best choice. This allows you to tune your Lambda functions for the metric that's most important to you. If you have a synchronous process, you may want to choose the one that executes most quickly so that your customer has the best experience. Meanwhile, if you're executing a back-end process and completion times are less important, you may want to allocate less memory and pay less for your functions. In this case, we see that there's a difference of 10 seconds in memory allocation, only for an increase that's very small. In this case, even if cost is your main metric, it may be worthwhile for you to apply the most memory. All of these are business decisions and are up to you, the customer, to make based on what's most important to you and your users. When we talk about permissions for AWS Lambda, we talk about two sides of the model. The AWS permissions model specifies a function policy and it specifies an execution role. The function policy allows you to control what resources, services, and users can invoke your Lambda function. Resource policies can be used for cross-account access, and they're used for both synchronous and asynchronous invocations. The second part of the Lambda permissions model is the execution role. This determines what your Lambda function can do at runtime, what resources it has access to. For example, you can provide read access to a DynamoDB table to your Lambda function without providing write access to that function. This allows you to create a very fine-grained model of security and enforces the least privilege principle. When building your serverless web application, you're going to rely heavily on Amazon API Gateway. Amazon API Gateway is one of those event sources that we mentioned earlier that can invoke your Lambda function. Amazon API Gateway is a fully serverless service. That is, it satisfies our 4 tenets of serverless. You only pay for the usage of API Gateway that you use. There's nothing for you to provision or no runtime to manage. API Gateway allows you to create a unified API front end for multiple microservices. These could be written as a collection of AWS Lambda functions, as AWS Fargate jobs, or as other resources. API Gateway provides DDoS protection and throttling for your backend, allowing you to save costs when you're under attack. API Gateway also provides tools that allow you to authenticate and authorize requests to a backend so that your Lambda function is not invoked when a caller is not authorized. And if it's not invoked, you don't pay for it. Finally, API Gateway allows you to throttle, meter, and monetize your API usage if you're providing an API to third-party developers. There are three key types of APIs available. There are edge-optimized APIs, which utilize CloudFront to reduce TLS connection overhead. This means you're going to see a shorter round-trip time. It's designed for a globally distributed set of clients. There are also private APIs, which are only accessible from within your VPC and networks that are connected to your VPC. These are designed for building APIs that are used internally or by private microservices. Finally, there are regional APIs. This is the recommended API type for general use cases. If you're building your web application and you don't have the constraints of the other two, you should generally be building with regional APIs. These are designed for building APIs for clients that are in the same AWS geographical region. When you look at an API gateway architecture, it looks similar to the event-driven invocation model. A client, such as a mobile client, website, or service, sends an HTTPS request to your Amazon API gateway, which then invokes a back-end service to fulfill that request. As discussed before, that request or that back-end service can be an AWS Lambda function, public endpoints on Amazon EC2, any other AWS service, or private resources, such as endpoints in your VPC, or even on-premises via AWS Direct Connect. In March of 2020, HTTP APIs for Amazon API Gateway became generally available. HTTP APIs allow you to achieve up to a 67% cost reduction and 50% latency reduction compared to REST APIs. They're also easier to configure than REST APIs, allowing you to focus more time on building applications for your users. This means that you can get up and running faster and see increased performance at less cost if you do not need all of the features that are provided by API Gateway's REST APIs. HTTP APIs form the core of what we see as the future of web applications. Your static assets, such as HTML, CSS, JavaScript, or even single-page applications, can be hosted on the AWS Amplify console. Authentication can be managed by Amazon Cognito. Your client connects to Amazon Cognito to authenticate itself and then uses the authentication information to make a dynamic API call over HTTPS to Amazon API Gateway. On the back end, API Gateway passes that request to your AWS Lambda function, which performs the read, write, or update to your Amazon DynamoDB table. Although we're focusing on web applications today, there are a few more serverless architectures that I'd like to make you aware of. First, you can use the S3 to Lambda model, a powerful invocation with many use cases. Anytime an object is uploaded to S3 buckets that match criteria you specify, a Lambda function is invoked. You can also invoke a Lambda function based on incoming data, whether that's to information published to an Amazon SNS topic or an event that's placed on an Amazon EventBridge event bus. You can also use AWS Lambda to poll an Amazon SQS queue. When messages are inserted into the queue, the polling service will pick them up and invoke your Lambda function for you. If you have streaming data coming in from Amazon Kinesis, that can also be used as a trigger for your AWS Lambda function on a polling basis, similar to SQS. And then finally, a use case like chatbots that we discussed before can make use of Amazon Lex. Amazon Lex will pass the intention into your AWS Lambda function, which allows you to perform some sort of compute in response. It's also worth noting that an event can just be the passage of time. You can use CloudWatch events, and when a scheduled time occurs, you can invoke your Lambda function this way. This is typically very useful for IT infrastructure management, tasks that need to be run on an hourly, daily, weekly, or other repeating basis. So we've discussed individual Lambda functions, but a business workflow is rarely a single function and it's rarely sequential start to finish. For example, you can have multiple branching decision paths in your application, multi-step processes that need to complete together, and a need to handle failure. AWS Step Functions allows you to do just that. It's workflow management with zero administration, and of course, it's a serverless service. AWS Step Functions makes it easy to coordinate the components of distributed applications and microservices using visual workflows. This lets you gain agreement with your business analyst that the code that you're about to write is actually the business process that needs to be supported. AWS Step Functions supports 7 different states, including several types of task states that perform service integrations. Step Functions logs the state of each step, both the input and the output, so that when something doesn't go quite the way you planned, you have the full event data there to help you diagnose and debug problems quickly. As I mentioned, Step Functions has several service integrations that can help you complete your work more effectively. They're listed on this slide. You can directly send a message to an Amazon SNS topic or place a message on an SQS queue. You can invoke an artificial intelligence or machine learning job on Amazon SageMaker, run an ETL pipeline in AWS Glue, run a long-running compute job with AWS Batch, launch a container on Elastic Container Service or ECS or Fargate, or you can do a data reduction job using Amazon EMR. AWS Step Functions with service integrations provide simpler integration with downstream services and allow you to write less code. Without service integrations, you have to write a polling model like you see on the left, and you have to write and maintain that yourself using AWS Lambda functions to get the job status, check if it's complete, if not, wait and retry, and handle failures. But as you see on the right, you can greatly simplify this workflow with a direct service integration. This workflow runs an AWS batch job synchronously. That batch job will have one of 2 outcomes. It will succeed or it will produce an error. Each outcome publishes its results to an SNS topic that you configure, and the workflow is complete. So as you're building your web application with serverless, you'll want to take advantage of the tooling that's out there. There's a number of different ways to build. This tooling will help you decide, where do you start? Our recommendation to you is that you start with a framework. Which framework you choose is less important than actually choosing one. You should choose the one that's most closely aligned with the programming languages that you're familiar with or with the knowledge of your existing team. AWS offers frameworks such as AWS Amplify, AWS Chalice, and the AWS Serverless Application Model, which we'll cover more specifically. There are also a number of third-party services that may meet your needs more closely. We'd encourage you to check those out as well. The AWS Serverless Application Model, or SAM, as we like to call it, is an AWS CloudFormation extension optimized to help you build serverless applications. That means it's just a superset of CloudFormation. Anything that's valid CloudFormation is valid SAM, but it also adds in special serverless resource types like functions, APIs, tables, Lambda layers, and serverless applications. This is an example AWS SAM template. In just 20 lines, you see that we've defined a Lambda function, an IAM role for that function, we've created an Amazon API gateway, and we've created a DynamoDB table. This brief template produces this complete architecture. But AWS SAM is more than just a CloudFormation transformation. AWS SAM also provides a command line interface, or SAM CLI as we call it. This is a tool that supports local development, debugging, testing, deploying, and monitoring of your serverless applications. When we say local development, we mean that it also supports API Gateway proxy style and Lambda Service API testing locally. That's right, you can run Amazon API Gateway locally on your machine to ensure that it's producing the responses that you expect. It uses an open source Docker Lambda image to mimic Lambda's execution environment in the Amazon Linux 2 environment typically, such as timeout, memory limits, and runtimes. And it can also live-tail production logs from CloudWatch logs. SAM CLI uses an open source Docker Lambda image to mimic your Lambda function's execution environment, including the operating system and such settings as timeout, memory limits, and the runtime that you've chosen. SAM CLI can give you a live tail of production logs directly from CloudWatch logs so that you can see what happens on your machine as your function is invoked. And it can also help you build in native dependencies because that Docker image that it's running is running a version of Linux that's compatible with what your Lambda function will actually deploy in when it's deployed to your AWS account.
Let's use another demo to show how easy it is to get started building your serverless application with the AWS SAM CLI. These instructions for installing the AWS SAM CLI will be provided to you as links in the chat. Once SAM CLI is installed, simply type SAM init. This gives you the choice between an AWS Quick Start template or a custom template location that you specify. We'll choose the Quick Start templates, and Node.js is our runtime. You can choose whichever runtime you're most familiar with. We'll accept the default project name, and SAM creates the app for us. We'll change into the app folder, build our app, and go ahead and begin deploying it to our AWS account. We'll use SAM's guided deploy option. This walks us through the parameters required for uploading our app to our AWS account. We'll accept all of the defaults, including the stack name, region, not to confirm changes before deploying, allowing the SAM CLI to create an IAM role for us, and we'll save these arguments to a config file. This means in the future we can just run SAM deploy. While that uploads, let's look at what SAM CLI is built for us. In our SAM template, we see that we have a single AWS Lambda function, the Hello World function. We also see in the events section that it's connected to an API gateway endpoint at hello, which accepts the HTTP GET method and invokes our function. Further down in the template, we see our outputs, including the Hello World API URL, which gives us the URL for invoking our function, which we can use to test it. If we look at our app, we see that we have that single handler function, which accepts the incoming event, creates a response object, and returns it to API Gateway to be passed back to the caller. Now that our app is finished deploying, we see that we were provided that Hello World API output, which contains the URL we need. We can copy this output and paste it in our HTTP client of choice. You can use Postman or your browser if you prefer. When we access this endpoint, we see exactly what we expect. A JSON object is returned with a message, Hello World.
For more information on SAM, I'd encourage you to check out aws.amazon.com/serverless/SAM, as shown in the slide. An additional tool to help you get up and running with your own serverless web application is the AWS Serverless Application Repository. Here you can discover, deploy, and publish serverless applications. With recently announced organization support, you can share the applications that you create across the accounts in your organization, but it's also useful as a learning tool. You can look at the source code for applications that have been published to the Serverless Application Repository and learn how other developers are building their serverless applications in the frameworks and runtimes that you've chosen. Now that we've chosen a framework and deployed our function to our AWS account, it's important to understand what that function is doing in our account. We do that with observability. Observability answers the basic question, how do we measure this? How can we measure the performance impact of the code that we're executing? Our position is that metrics, logging, and tracing are universal rights. To help support you, we've built in CloudWatch metrics. CloudWatch metrics gives you 7 built-in metrics for AWS Lambda: the invocation count, duration, any errors, any throttled invocations, the age of your iterators, any dead letter queue errors, and your concurrency. You can also call put metric data from within your Lambda function code for custom metrics. And these custom metrics will appear in CloudWatch. CloudWatch also provides you 7 built-in metrics for API Gateway. These metrics track the API calls count, latency of your requests, 400 series errors, 500 series errors, integration latency, your cache hit count, and your cache miss count. The error and cache metrics support both averages and percentiles so that you can see what's happening in general for your users, but also in those worst case scenarios at P95 and P99 and beyond to understand how you can better optimize your calls. Metrics measure what's happening, but logs give you the information to know what happened with context. CloudWatch Logs offers API gateway logging with both error and info logs, and optionally allows you to log your method request and body content, a great feature for your sub-production environments when you're trying to understand what's happening. You can set these logging options globally in the stage, or you can override them so that only certain methods in your API have this logging enabled. Lambda logging provides basic logging directly from your code with your language's equivalent of console.log or funct.println in Go, print in Python. You can also do structured JSON logging with the embedded metrics format to give yourself more easily machine-readable logs. Log pivots are a feature of CloudWatch Logs that allows you to build metrics based on log filters, and it jumps to the logs that generated the metrics, allowing you to understand what's happening with your invocations in the aggregate. And finally, you can export your CloudWatch logs to AWS Elasticache or S3 so that you can search through them and explore what's occurring with tools like Kibana or Amazon Athena or Amazon QuickSight. So that's metrics and logging, but for tracing, we also provide AWS X-Ray. AWS X-Ray is a tracing service that profiles and troubleshoots your serverless applications, and it can be invoked in two ways. One, you can set active tracing in a SAM template, for example, and that gives you information from the outside about your function, how long its invocations take, or whether it returns errors. You can also do instrumentation inside your code by including the X-Ray SDK, as shown on this slide. That allows you to time specific calls or provide specific metrics back to AWS X-Ray that can then be aggregated, graphed, and examined. API Gateway inserts a tracing header into HTTP calls, as well as reporting data back to X-Ray itself. This allows you to aggregate HTTP calls and the Lambda functions that supported or fulfilled them so that you can get end-to-end tracing for your user requests. In this slide, we see an example of an X-Ray trace. This is our S3 example AWS Lambda function, and we see that its first attempt took 1.8 seconds to complete. We see that attempt broken down further into initialization and S3 API calls, which resulted in a 404. We see that our status is highlighted for us. That put object call did not succeed. We can begin our investigation here. AWS X-Ray provides more than just per function tracing. It also provides analytics on that tracing over time. On this slide, we see that we received a set of traces, over 10,000, but we've been able to filter them based on some criteria that we specify into two sets. This is, for example, blue-green testing or A/B testing that allow us to see how different changes to our entire application resulted in different invocation errors or different execution times. So before we get into our question and answer period, I'd like to review what we've learned today. First, we discussed what is serverless. What do we mean when we say serverless? What are some key serverless concepts that you need to understand to build your first serverless web application? What are the execution models that we use with AWS Lambda, and which ones would you choose given your specific use case? We've covered pricing and resource allocation, allowing you to tune your Lambda functions to meet your business needs. We've covered permissions for AWS Lambda functions and understanding both what can invoke our function and what our function can access while it's executing. We covered Amazon API Gateway, the front end for your serverless web application that allows you to handle incoming requests from your clients. We covered some tooling and how you'll want to be using a framework when you're building your serverless web application. And finally, we discussed observability with metrics, logging, and tracing. If you'd like to learn more about serverless at AWS, I'd encourage you to visit aws.amazon.com/serverless. You'll want to bookmark this page and return to it often as you build to get answers to the questions that come up and to better understand how the different serverless services integrate with one another. And if you haven't yet chosen a framework, I'd suggest you check out SAM, the serverless application model. The URL presented on this slide will take you to the SAM homepage, where you can learn how to create an application, how to deploy your application, and the new features that we've provided. I'd like to thank you all for joining us today. It's been my pleasure to be here with you. And at this time, I'd like to open up and take your questions.